Hello there, let's continue our look into entropy. Today's lesson called Calculating Changes in Entropy. We're going to calculate the entropy change for a reaction and interpret the value to determine if a process will be spontaneous or not. Up until now, in the last couple of videos, we've been exploring entropy very conceptually, trying to wrap our heads around what it is, what it means when it's said that it's a measure of disorder. Today, we're finally going to start putting some numbers, some cold hard numbers behind it all, and looking at how we can calculate entropy and what that can infer about a chemical reaction and this idea of feasibility or spontaneity. So, we've been saying again and again that entropy is a measure of disorder in a system. All systems gain entropy over time because this is a more likely outcome. We've been exploring this, like I say, in the last couple of videos, seeing that disordered outcomes are just statistically more likely to occur than ordered outcomes. So over time, entropy will always increase. Disorder is a more likely outcome as the system becomes more disordered, it becomes more energetically stable. Last time we compared the change, so the difference between the products and reactants on a conceptual level by looking at, gas molecules being produced or not being produced, looking at the complexity in molecules being produced or substances being produced, the hardness, so on and so forth, and inferring what this means about the microstates and therefore the changes in entropy. But we can put some cold hard numbers, like I say, behind this if we have entropy values for the reactants and the products. So this is an equation we can use to calculate the entropy change for a system. Now it's very similar, we've seen something very similar to when we were calculating enthalpy changes for a system. If we want to know the change, so that sign delta means the change. If we want to know the change in entropy at standard conditions, we got our plimsoll sign there. For a system, where our system in this instance is our chemical reaction, well, just like we've done with our enthalpy changes, we can look at the enthalpy after the reaction, look at the enthalpy before the reaction, and quite simply see how it has changed. So this funny looking symbol there, this is what's called a sigma sign. This means sum of. So we get the sum of the entropy of all the products and we subtract it from the sum of the entropy of all the reactants, and that's going to give us the change. Hopefully you can follow the logic there. So to calculate the delta S of the system, there's a few things you need to consider. You need to take into account the equation's stoichiometry, similar to how we've seen the delta H calculations. We'll do an example of this in just a moment, so I'm sure it'll all come refreshing back. And we can use entropy values. These are given to you. You're not going to be expected to memorize entropy values. They're going to be provided, and then you've just got to apply them to calculate entropy changes is the important thing. You need to choose data from the correct state. So if we're in our standard conditions, we've got to select the appropriate value. So here's a question, as always. If you want to just dive on in, I've given you an equation up here, I've given you a reaction here, I've told you to take into account stoichiometry, and I've given you a bunch of entropy values there. Why don't you just dive on in and give it a go, and then we can check it now. So what I'm going to do is I'll rewrite the equation up here so I don't have to keep flipping back. Got the classic combustion reaction of methane gaseous plus 2O2, so that's what we're talking about with the stoichiometry, the good old balanced chemical equation. Combustion reaction, let's assume complete combustion, we're forming carbon dioxide and water vapor. All right, so we've said that the delta S of the system of this chemical reaction is going to be the sum, if I can do a sigma sign, there we go, the sum of the entropy of the products minus the sum of, I struggled with that, sum of the entropy of the reactants. So let's get into it. Let's have a look at what our products are. Well, we've got a carbon dioxide. We've got the entropy of carbon dioxide just there. The standard entropy at standard conditions of carbon dioxide gaseous is 213.6 joules per Kelvin per mole. So we can chuck that in there. 213.6 for our CO2. In fact, what I might do is I might write it out with all the symbols and then we'll plug the numbers in. So we need the entropy of carbon dioxide for the products plus the entropy of the water. But this is what I'm saying, it's really important to account for the stoichiometry. We don't just have one water, we have two waters. Two waters means more microstates, means more disorder possible, so on and so forth. So we have to account for that by getting 2 times the entropy of H2O, like that. So that is our entropy of our products there. Now we're going to subtract that for the entropy of our reactants. I'm going to move down here because, as you can see, I'm running out of space on my page. So minus the entropy of the sum for the reactants. So we've got a standard entropy for methane, CH4, plus, again, 2 times the entropy of our oxygen, because we have 2 of them, like that. Now we can just plug and play using the values that are given. To reiterate, you're not expected to memorize these values. They are certainly going to be given to you. More important things to keep in that brain case than a whole bunch of random numbers. So what have we got first of all? We got carbon dioxide, which is 213.6. Then we've got 2 times the water. Where's our water? 188.7, if I can remember that, plus 2 times 188.7. So that there, I might get some colors in here just to really highlight what I'm trying to show. So that's the sum of the products of, that's the sum of the entropy of the products. And what we're going to do is we're going to subtract that from the sum of the entropy of our reactants, which we said was the entropy of methane. Entropy of methane being 186.2. 186.2. And then the sum of, with the 2 lots of oxygen, we have 2 times 205.0. 2 times 205.0. And that there, if I get a different color, or maybe something a bit different than orange, it's a bit close to red, let's get a lovely purple going. That is the sum of the entropy of our reactants there. Boom. So now, as we do with these equations, just a matter of plugging and playing. Making sure you got all your brackets going on. 213.6 plus 2 lots of 188.7. And we're going to subtract that from 186.2 plus 2 lots of 205 to give us an answer of minus 5.2. Minus 5.2. What are our units? Our units of entropy are joules per Kelvin per mole, like that. So that there is going to hopefully be our answer in this equation just for the system. So what is this value telling us? You know, it's one thing to get a number, but we've got to work out what that number is telling us. Otherwise, that number is useless. So this number here has a negative sign. We're dealing with changes. This is telling us that it's decreasing. The change is going down. That tells us that we're having a decrease in entropy. And in fact, that's telling us that it's actually getting more ordered, because if we're decreasing entropy, it's getting more ordered. We've also got a value of 5.2. That's telling us how disordered it's getting or not getting. And you know, that's quite a small number. So this is saying we're actually having a very small increase in order. We're having a very small decrease in entropy. Now we can think about this conceptually as well, using what we discussed last time. If we didn't do any of this math and we just looked at this equation, we could compare the products to the reactants. Predominantly, we focus on the gaseous molecules. We've got 1 plus 2, we've got 3 gaseous molecules in the reactants. We've got 1 plus 2, we got 3 gaseous molecules in the products. Now looking at those molecules, you know, there's nothing particularly more or less complex than the other. So this one would be a difficult one to predict if we're going to have an increase or decrease in entropy. So that's why we've sort of got a small value there. And when we put all the maths in, we've actually got a small decrease in entropy, meaning it's getting more ordered. A little bit counterintuitive. We might think of combustion reactions as, you know, being spontaneous reactions. In fact, I even used it as an example of reactions that very much do increase entropy. And they do, because this is only accounting for one factor in our total entropy changes. We've got the entropy of the chemical reaction. Are the reactants getting more complex? Is there more microstates from the products? But there's another thing that you have to consider, and that's the energy that is given off or the energy that's taken in, because that's going to affect the complexity of the surroundings. So this tells us the value for the change in entropy of just the chemical reaction. But if we want to know the total entropy change, we've got to not only consider the system, but we've also got to consider the surroundings, because the entropy change is a measure of the dispersal of energy, which includes whether that's going to be an endo or an exothermic reaction and the effect it has on the surroundings. So how have the surroundings changed in energy? We've got to go back to our old friends, endothermic and exothermic reactions. To remind you very quickly, exo, the energy is exiting, the energy is transferred from the systems to the surroundings. So our reactants have a higher energy than our products, and that energy difference is being dispersed to the surroundings. Whereas endothermic, you can think of the energy entering, the energy transferred from the surroundings to the systems. So our reactants have a lower energy than our products, and they're getting that energy, taking it from the surroundings. So again, entropy is a measure of energy at a specific temperature. So whether we're taking energy from the surroundings or putting energy into the surroundings is very much going to affect the total overall entropy change, not just with the microstates within the actual chemical reactions within the reactants and products themselves. So we can consider entropy as a dispersal of energy either from the system to the surroundings or from the surroundings to the system. And so far we have only looked at the systems, and we've got to look at the surroundings as well. Need to consider both the entropy change of the system and the entropy of change of the surroundings to determine if the total entropy has increased, thus it will be a favorable reaction, or if the total entropy has decreased, thus an unfavorable reaction. Going back to all that stuff we've been talking about, the idea if that entropy increases, it gets more disordered, favorable. Entropy decreases, it gets less disordered, unfavorable. More or less microstates accordingly. So we've only been looking at the ΔS of the system, which would tell us that this is actually an unfavorable reaction. But what we'll see is when we start to incorporate the ΔS of the surroundings, we're going to see a very, very different idea, because our combustion reactions are very exothermic. They give off lots of heat. We looked in the previous lesson, we looked in the previous lesson, the relationship between entropy and temperature. And very much as temperature increases, our entropy increases, because I'm going to keep saying it, more microstates, more possible arrangements, more disorder. If entropy change increases, the change will be positive. So if the total is positive, the reaction will occur spontaneously and it can be said to be feasible. If the entropy change decreases, the change will be negative and the reaction is unlikely to occur. So a total increase in entropy, more disordered. A total decrease in the change in entropy, more ordered. Now this idea of feasibility and spontaneity, something we're going to come back to later on, but I'm going to say it now. Just because a reaction is feasible, it just means that it can occur. Doesn't mean that it will occur. We'll talk about what that means a little bit more later on. So let's have a look at how we can calculate the entropy change of the surroundings. Well, it's going to be determined by if we have an exothermic change, we're giving off heat, or an endothermic change, we're taking in heat from our surroundings. If energy is being released to the surroundings, what is that going to do to the entropy of the surroundings? Have a think. Hopefully what you arrived at is that the energy will increase. We'll increase the number of ways to arrange this energy. Just going back to all that relationship between entropy and temperature. Covered it a lot in the previous video, so very much go and revisit that one to consolidate your relationship between those two factors. But yeah, if we're making the surroundings hotter, we're going to increase the number of ways this can be arranged, and we're going to have more microstates. So there's likely to be an increase in entropy and therefore a higher chance of the reaction occurring spontaneously if we have an exothermic change, when we're just considering the ΔS of the surroundings. Conversely, the endothermic change is doing the opposite. It's taking energy from the surroundings. You know, our surroundings can be the water molecules if we're doing it in a wet chemistry, or whatever, our solvent if we're doing it in a solvent. It can be the air particles. But if we're taking the energy from those surroundings, we're making less microstates. Therefore, we're making it more ordered. So energy absorbed will decrease the number of ways to arrange this energy, which means less microstates. So likely to be a decrease in entropy if we have an endothermic change when we're looking at it from the perspective of the surroundings. lower chance of the reaction occurring spontaneously. All right, we keep saying that as we know, entropy is the measure of the dispersal of energy at a specific temperature, which we have been writing as our entropy. Entropy is the dispersal of energy per temperature. Well, what's the factor that is determining the energy that's given off or given in or taken in? It is the enthalpy change. So our Q is coming from our delta H. That's where the energy is coming. Is that energy taken in, or is that energy taken out, given out? So we can calculate the delta S of the surroundings via this equation, where we pop a negative sign in front of it for reasons I'll discuss right now. So we can calculate it like this. The delta S of the surroundings is taken into account the enthalpy change, and then, as we keep saying, entropy is a measure of energy at a temperature. We've got to consider our temperature. If we're at standard conditions, our temperature is going to be 298 kelvins, because that is our standard conditions for temperature. Also, very important to note, our delta H's are often given as kilojoules per mole, whereas our entropies, so this is our delta H's, are often given in those units. But our entropies, as we've been seeing, are joules per Kelvin per mole. So we have an incongruency between our units, between the entropy and the enthalpy. So very important, if the enthalpy is in kilojoules per mole, we need to multiply by 1,000 to make sure that the units are congruent with one another and can be used in this equation together. So why is that minus sign there? Well, we said that a exothermic change with energy being released to the surroundings is very much going to increase the entropy of the surroundings. More microstates, more disorder. So if we have an exothermic change, we need to end up with a positive value for delta S, because that's saying an increase in entropy. But we know that exothermic changes have negative delta H's. So if you go a negative number divided by a positive number, because our T is 298 at standard conditions, and also Kelvin's, can only be a positive number because 0 is the absolute zero value you can have. Well, that's going to end up with a negative value. So we've got to pop another negative in front of it. Negative times a negative gives us that positive, that increase in entropy for exothermic. And then similarly for the endothermic change, we know that endothermic changes have, I wanted a different color. Endothermic changes have very much positive delta H's, but we know we've got to end up with a negative value for our delta S, because we're taking the energy out of the surroundings, we're making it more ordered, we're decreasing the entropy. So for the same reason, pop the minus sign, minus times a positive gives us a negative. So by having that negative sign in front of it to calculate the delta S of the surroundings, that means that all our exothermic and endothermic changes are going to be consistent with what we know about entropy. Let's plug some numbers. Calculate the delta S of surroundings for the following reaction. Oh, similar looking reaction. In fact, it's the one we just did, which we calculated the delta S of the system. Now we're doing it for the surroundings. I've given you a delta H, I've given you a temperature, standard conditions, plug it in, see what you can come up with. Check it now. Let's go down. So we got the delta S of the system. I wonder if, oh no, we'll just go down here. Keep it nice and simple. Let's get the delta S, standard conditions of the surroundings. Surroundings. So we said that's equal to minus delta H divided by T, where our delta H value is equal to minus 890.8 kilojoules per mole. Minus 890.8 kilojoules per mole. We said it cannot be in kilojoules because our delta S is in joules. It has to be all consistent, so we're gonna have to multiply that by 1,000 to make it joules per mole when we're plugging it in our equation. So let's do all that now. Minus, why am I doing a delta sign? Minus 890.8 times 1,000 divided by a temperature, which is 298, equals, as we do, calculator, plug it all in, minus 890.8 times 1,000 divided by 298 gives us an answer of positive 2989.3 joules per Kelvin per mole. What is this value telling us about the chemical reaction here and entropy? Similarly to how we analyzed what the negative value means for the delta S of the system, when we look at the surroundings, we're having a positive value. We're increasing the entropy of the surroundings. And that makes sense. We're giving off all that heat. You know, you think about that huge enthalpy change, all that energy is being released to the surroundings. Let's say in this instance, we're burning the methane in air. All that energy is going to the air particles. They're getting all that energy. They're increasing temperature. They're getting more entropy. We are having a really, really big entropy change when we consider how the surroundings are changing. Plus 2989.3 kilojoules. Sorry, 2989.3 joules per Kelvin per mole. There we go there. Our chemical reaction doesn't just happen in isolation. We can't just consider how the entropy changes between the reactants and the products. Also need to account for how that entropy is going to affect its surroundings. So when we talk about the total entropy change, we're taking into account both of these factors. So let's put them together for our methane combustion reaction. We have calculated now an entropy change for our system, where we're saying, looking at the reactants to the products, there's actually a small decrease in entropy when we change these products to these products. And then we looked at the surroundings. When we consider the energy that is given off in this reaction, we have a very, very large increase in the entropy of its surroundings. So its total is the system plus the surroundings. Give it a pause, plug it in. Nothing too complex there. If we've got a value for the delta S of the system, well, our total entropy change is going to be minus 5.2 plus 2989.3. And what we end up with is a total entropy change, which is very, very large. So it's quite interesting, right? The fact that, you know, the entropy change of the system and the surroundings in this combustion reaction, they're almost working counterintuitively to each other. So it's both these factors that are going to affect if we have a overall increase in entropy. You know, if the system increases entropy and it also increases the entropy in the surroundings, that's going to very much be a very favorable reaction. If the system is decreasing entropy and we're also decreasing entropy in the surroundings, that's very much going to be very unfavorable reactions. Where it gets interesting is where one is increasing the entropy and the other is decreasing the entropy, which is what we saw here. So our chemical reaction decreases the entropy, whereas our energy change for the surroundings is actually increasing the entropy. And because this is so much larger than that, we end up with actually a very spontaneous, very feasible reaction. So let's talk about that idea of feasibility. We mentioned it earlier just before. Remember, changes that increase entropy are energetically favorable. The system becomes more energetically stable when it becomes more disordered. Our total entropy change, as we've now seen, considers both the entropy change of the system and the entropy change of the surroundings, where our delta S of the surroundings is dependent on temperature. So our value for the delta S of the total can be affected by changing the temperature. We've just been looking at standard conditions, but we can very much see that our delta S of the surroundings is influenced by temperature. So we can make the reaction more or less feasible by manipulating the temperature as well. Just an important thing to note in there. So overall, to summarize this, for a reaction to be feasible, we need to see an increase in entropy. Thus, we need to have a positive value for the change in entropy, because that's telling us that the change is increasing. We're having a positive, we're having more disorder. Disorder is energetically favorable. The larger this value is, the more feasible it becomes. So, you know, compare a delta S for a reaction for the total, something which is plus 10 compared to this one here, which is plus 2,000 or closer to 3,000, isn't it? You know, we're very much going to be very confident that this is going to be a very feasible reaction. But that word feasibility, you'll also see spontaneous, feasible, spontaneous, both describing the same thing. It just means that it can occur. Doesn't necessarily mean that it will occur. You've got to consider things like activation energy. A reaction might be very feasible, but it might never actually happen because it's got a high barrier for the energy to activate that reaction. Feasibility and spontaneity also doesn't mean that it happens quickly. We can have very, very slow reactions that are spontaneous as well. All it means is that it can occur, it's energetically favorable, and that if it begins occurring, it will continue to occur of its own accord. But there we go. Once a feasible spontaneous reaction does begin, it will continue of its own accord until the reactants run out. Let's finish up by a final discussion looking at something that up until now I've quite conveniently been ignoring. That's the idea of reversible reactions. We've only been looking at reactions that proceed in one direction, but we know that we can have equilibrium reactions, reactions that have forward and backward reactions both occurring. So far, I've been discussing entropy changes for irreversible processes that have one direction that increases entropy and one direction that decreases entropy. But what about our equilibrium reactions where both forward and backward reactions occur? We remind ourselves about the idea of equilibrium in reversible reactions. It's the point at which the rate of the forward reaction equals the rate of the backward reaction. So we have no overall observable change, but both reactions are very much still occurring. Does this mean that both, we're increasing entropy in both directions? How does that work? That runs very counter to what we've been saying. So let's explore this idea. When a reversible reaction begins, we see an initial increase in entropy can occur. So as our reactants turn into the products, we increase entropy, which is energetically favorable. But as that reaction proceeds further and further, the disorder begins to decrease, which means that the backward reaction is then going to be the more favorable one, because if disorder is now decreasing at a certain point, that means the backward reaction is going to increase, and that's what's observed. Then consider the backward reaction. That begins to increase disorder until it doesn't, until the disorder of the backward reaction begins to decrease. So then there reaches a point where it decreases. So at this equilibrium position, it's reached when the rate of the forward reaction is equal to the rate of the backward reaction. So in terms of entropy, the entropy change of the forward reaction is going to be equal to the entropy change of the backward reaction. And what this means is that the overall entropy change in an equilibrium reaction is going to be 0. We've said that the total entropy change is equal to the entropy change of the system and the surroundings. So looking at standard conditions for a system at equilibrium, the overall entropy change is going to be 0. So the system and the surrounding, the changes in entropy is going to equal 0. This very much fits in with what we've been looking at with the second law of thermodynamics, the idea that entropy is always increasing. Well, entropy can't decrease, and in a equilibrium reaction, entropy isn't decreasing. It's just remaining constant, which is still abiding by that second law of thermodynamics. So to summarize it all, irreversible reactions that occur in one direction increase entropy. For a system at equilibrium, i.e. our reversible reaction, the entropy will remain constant, which is the important factor. And that concludes this lesson. What have we done? We've calculated the entropy change for a reaction, delta S, given the standard entropies of the reactants and the products. And then we took that a step further and looked at how the entropy of the surrounding and the system is interrelated. Tasks. Pause now, work through those one column at a time, from the bottom to the top, to consolidate and practice the key concepts we've covered in this lesson. Thank you very much for your time. Look forward to next time when we reach the tail end of our look into entropy and our look into chemical energetics. See you later.